Alright, we're back and we're looking at motion in 2 dimensions. We've looked at motion in 1 dimension in past videos, and we've looked at the kinematic equations and how to use them. If you haven't seen those videos, or you haven't, obviously, you don't necessarily need to watch those past videos. Maybe you already get it. But if you haven't kind of figured out the intuition behind these, I definitely recommend going back and watching those videos or reaching out to Ahab and asking him for help. So now that we know these kinematic equations, we're going to apply them into 2 dimensions. And so we've got our x dimension and our y dimension. And you remember in motion with on one dimension, it was kind of easy to not have to deal with vectors because all of the vectors that we were dealing with were all on one line. And that's kind of like the number line, you know. You can always add 2 plus 2 because, well, they're on the same number line, just like you can always add 2x hat to 2x hat because they're on the same number line. Well, now we have 2 number lines, and the most important thing to remember in motion in 2 dimensions is that you cannot add y components with x components. You cannot add orthogonal quantities or orthogonal vectors. So the idea here is here's our equations kind of in their standard form. You may see them written differently. I know everybody has them written a little bit differently and using different symbols. I just recommend that you find a method that works for you and stick with it. That's kind of what I've done. These are how I write them out now. I think it's pretty close to the way Ahab writes them as well. So now that we have 2 dimensions, we need to keep our equations straight. So our x-axis equations and our y-axis equations should never be mixed. So in other words, each one of these equations only works in 1 dimension. And so you can't put acceleration in the x direction here and then have velocity initial in the y direction. Everything in here must be a subscript x, or it must be in the x direction. So if I were to write at plus vi equals vf, I would write it for the x-axis, I would say a sub x. And what that represents is the x component of acceleration times t. Now, lucky for us, time is in a whole different dimension, so we don't really have to worry about time because it's a scalar. So we don't need to have t sub x or t sub y. And then this is going to be plus v initial in the x direction equals v final in the x direction. And you'll find a nice way of notating it for yourself. I like to say the initial sub x. It just reminds me that I should not be adding y components to that. And then, of course, if I write it for the y-axis, this would just be a sub y times time plus vi sub y equals vf sub y. So this is just to keep things straight in our head. Notation's really important. A good notation will set you up for good homeworks, good test scores, just keeping things straight and methodical. All right, so the next thing I wanted to talk about, and once again, you can write any of these equations in terms of sub x's or sub y's. And remember, there was just a video on vector addition. There's already been a chapter on vector addition, and so this is going to be very important to know how to add and subtract vectors. So let's take a look at one of the most popular problems that's going to, well, in physics really, it's called projectile motion. And what projectile motion is there's only acceleration in one direction. There's acceleration in one direction. We call that acceleration g. It gets a special letter because g is the gravitational acceleration on the surface of planet Earth. And it's roughly, let me write this, it's an estimation, but it's roughly 9.8 meters per second squared. Some people say 9.81. You could definitely do that. So anyhow, the cool thing about Earth's surface is that even though it is, curved, with any reasonable distance that we observe things, it seems pretty flat. And so you can assume that if you're on Earth, and let's say x equals 0 is the surface of the Earth, there is the same acceleration vector at every given point that you can think of near the surface of Earth. And so there's this field, this gravitational field, and it causes acceleration to objects with mass. Alright, so now that we know that there's this field here, we also know from Newton's from Newton's first law is that an object in motion tends to stay in motion, and also an object that is at rest tends to stay at rest. And so that's an important concept, because without this gravitational field, let's imagine we're like in deep space. If something was moving in this direction, it would just keep moving in that direction until it was acted on by an outside force, because there is no gravity there. And so, as you can see, it would just keep moving in a straight line until something affected it. Now, whereas in this gravitational field, if you were to throw something, so if we were in deep space, that something would just go in a straight line forever. But because we're on Earth, what happens is when you throw something, it gets deflected downwards in the y-axis direction by gravity. And what you end up with is a shape called a parabola that you've probably spent a lot of time with in algebra. And so the interesting thing here is, and this is a really nice trick to know, is that if I were to look at any point at all along this trajectory, each point would have an equal velocity in the x direction. So all these velocity vectors are the same length, so the x velocity isn't changing, which makes sense, right? Because when there's no gravity, things will just go in a straight line at the same velocity. Well, gravity is acting in the y direction, and so the y is deflected, the y-axis velocity is deflected with acceleration and caused to go down. But remember, we cannot, orthogonal vectors like this aren't going to affect each other in the gravitational field. So the velocity in the x will remain to be the same velocity from takeoff to landing. And that is an approximation because air resistance, other things that might happen. But pretty much the x, and especially in reference to this course, the x velocity is never affected by gravity. It's only the y velocity. So this is kind of what projectile motion looks like. Let's go ahead and take a problem on it. So I'm going to go ahead and say, let's use this graph here, and we're going to do a similar problem. So starting at the origin, let's say that I have projected something at an angle of, let's say, 45 degrees, and I've given it an initial velocity in that direction. V initial equals, let's say, 5 meters per second. So we kind of know intuitively what's going to happen here because of projectile motion and gravity on the surface of the Earth, is that this thing's going to come back down. Well, it's important though at first, because remember, x is not affected by gravity, y is affected by gravity. So we want to separate the x's from the y's. And so I'm going to draw this velocity right here. It's 5 meters per second. But now I'm really curious. I want to find, because this is my velocity total initial, I want to find my initial velocity in the x direction. And I want to find my initial velocity in the y direction. v initial y. And then I can start using these equations to solve the problem. But the first things first is I need to change my velocity, my total velocity, into components of velocity. And to do that, we're going to have to take a look at right triangle. Once again, they keep coming back up. So if this is the hypotenuse, in this case we'll call it VI, and this is VIY, and this is VIX. What we're going to do, and of course we've got angle theta, what we're going to do to find what VIX is in terms of VI and what VIY is in terms of VI is we're going to use trigonometric identities. If you remember, this side is called the adjacent, this side is called the opposite, and this side is called the hypotenuse. And as we know, sine of theta equals SOH, right? S-O-H, opposite over hypotenuse. So if I wanted to solve for the opposite side, in this case VIY, I would go ahead and multiply the hypotenuse over. So hypotenuse times sine theta equals the opposite. And in this diagram of velocities, the opposite is equivalent to VIY, and the adjacent is equivalent to, and the hypotenuse is equivalent to VI, or the total initial velocity. So this is how we solve for VIY. So VIY equals VI sine theta. And I just wanted to show this, building it from the trigonometry up. You're just going to learn to memorize this eventually, because it'll save a lot of time. So my next side is the adjacent side, and I know that cosine is a ratio. Cosine of theta is a ratio of the adjacent over the hypotenuse. So the adjacent is VIX, and the hypotenuse is VI. So this is my velocity initial in the x direction. This is my total initial velocity. I can multiply it over and solve that VIX equals the total initial velocity cosine theta. So the adjacent side is always going to be the hypotenuse cosine theta, and the opposite side is always going to be the hypotenuse sine theta. So that's how I'm going to break this down. Now I know that my angle is 45 degrees, and so using these identities, VIY equals VI sine theta. VI is 5 meters per second, and theta is 45 degrees. And then of course VI is 5, and cosine theta is cosine of 45 degrees. So now I've taken my velocity and I've broken it into components. This is the first step of solving a problem. You're going to use it every single time you solve a problem, most likely, that's in 2 dimensions with projectile motion. But this video is getting a little long. I think I'm just going to end it now, and then in the next video we can talk about how we can use these components and these equations to solve different sorts of problems. I hope this was helpful, and I'll see you next video.